Hello, and welcome to Space for Sleep. There is a question hidden behind almost every map of the cosmos. It appears whenever a telescope reveals a galaxy farther away than any galaxy seen before, whenever a new image reaches deeper into ancient light, and whenever a number, such as 93 billion light-years, is used to describe the visible universe. What happens at the end? The instinctive picture is simple. Space stretches outward for an unimaginable distance, becomes darker and emptier, and eventually reaches some final border. Perhaps there is a wall. Perhaps there is a thin membrane. Perhaps there is a black emptiness beyond the last galaxy. Perhaps the universe is suspended inside something larger, as a bubble hangs in air. Every part of that picture feels natural, because nearly everything encountered in ordinary life has an edge. A room has walls. An island has a coast. A cloud thins into clear sky. Even Earth, once imagined as an endless plain, turned out to be a finite object floating in space. It seems reasonable that the universe should also finish somewhere. But the universe is not an object placed inside space. It includes space. That difference changes the question completely. Suppose a spacecraft could move without needing fuel, without being damaged by radiation, and without being limited by the lifetime of its crew. It leaves Earth and travels in a perfectly straight line. It crosses the Milky Way, passes through the local group, leaves the nearby clusters, and enters the great filaments and voids of the cosmic web. It continues for millions of years, then billions. The galaxies behind it grow faint. New galaxies appear ahead. What would eventually stop it? The first obstacle would not be a wall. It would be time. The universe changes while the spacecraft travels. Space expands. Distant galaxies recede. Light moving toward the traveler follows paths through a geometry that is stretching beneath it. A destination that appears reachable when the journey begins may become unreachable long before the spacecraft approaches it. The second obstacle would not be distance in the ordinary sense. It would be causality. There are regions of the cosmos from which a signal can reach Earth today. Regions from which a signal emitted today will reach Earth only in the remote future, and regions from which no signal emitted now will ever arrive. These boundaries are called horizons. They are not made of matter. They do not glow. Nothing announces the moment one is crossed. They are limits created by the history of cosmic expansion and by the finite speed at which information can travel. The third obstacle would be the shape of space itself. A straight path may not behave as intuition expects. In a curved or multiply-connected universe, traveling steadily in one direction might never lead to an edge. It might lead back toward the starting point, or space might continue without end, or it might be finite while still having no boundary at all. The true edge of the universe, if the phrase has any physical meaning, is therefore not one thing. It can refer to the farthest light visible now. It can refer to the farthest region that will ever communicate with us. It can refer to the global size and shape of space. It can refer to the earliest time from which any information survives. These are different questions, and they have different answers. The clearest place to begin is not at the farthest galaxy. It is with a beam of light. Light does not arrive instantly. The moon is seen a little more than 1 second in the past. The sun is seen roughly 8 minutes in the past. The nearest large galaxy, Andromeda, is seen as it was about 2.5 million years ago. A galaxy 10 billion light-years away is seen not as it exists now, but as it existed during a much younger stage of cosmic history. A telescope is therefore also a time machine, though only in one direction. Looking farther away means looking farther back. The night sky is not a single present moment spread across space. It is a layered record of many different ages. This creates the first meaning of a cosmic edge. The universe has a finite age, close to 13.8 billion years. Light has a finite speed. There has not been enough time for light from every region of space to reach us. The boundary of the region that has had time to communicate with Earth is called the particle horizon. It is tempting to say that this horizon must be 13.8 billion light-years away. Light has traveled for 13.8 billion years, so the distance should be 13.8 billion light-years. But that would be true only in a static universe. The real universe expanded while the light was in flight. Imagine 2 points marked on the surface of a balloon while the balloon is being inflated. An ant walking from one point toward the other must cross a surface that is stretching during the journey. The separation between the points can grow even while the ant makes progress. The ant's travel time does not equal the present distance between the marks. The balloon image is imperfect because the universe is not expanding into a surrounding room. An ordinary three-dimensional space is not merely a surface. Yet the central lesson is useful. The distance between unbound cosmic regions changes while light travels between them. The oldest electromagnetic light visible today was released when the universe was about 380,000 years old. At that time, matter and radiation had cooled enough for electrons to join atomic nuclei. Before then, free electrons repeatedly scattered photons, making the universe opaque. After atoms formed, many photons could travel freely. Those photons have been moving through expanding space ever since. Today they arrive as the cosmic microwave background, a faint glow visible in every direction. The matter that released those photons was much closer to the region that would become the Milky Way than it is now. During the billions of years since the light began its journey, cosmic expansion carried that matter away. Its present comoving distance is about 46 billion light-years. That is why the observable universe is roughly 93 billion light-years across, even though its age is only about 13.8 billion years. This number is often misunderstood. It does not describe a ball of matter exploding outward from a central point into emptiness. It describes the present distance, in the standard cosmological model, to the most distant regions from which information has had time to reach us. Earth lies at the center of this observable sphere only because the sphere is defined around the observer. An observer in a galaxy 10 billion light-years away would also see an observable sphere centered on that galaxy. Much of it would overlap ours. Some regions visible to that observer would be permanently invisible to us, and some regions visible to us would be invisible there. No contradiction is involved. A horizon depends on where and when an observer exists. The ocean horizon offers a modest analogy. A person standing on a beach sees a circular boundary where sea and sky appear to meet. Another person far away sees a different circle centered on a different position. Neither circle marks the end of the ocean. It marks the limit of sight from that location. The cosmic particle horizon is far more profound because it is set not by the curvature of Earth, but by the history of space-time. Yet the same caution applies. A horizon is not necessarily an edge of existence. The best supported expectation is that the universe continues beyond the observable boundary. That statement rests on a quiet but powerful fact. Nothing unusual appears to happen as the most distant visible regions approach the horizon. The large-scale distribution of matter remains broadly uniform. The cosmic microwave background arrives from every direction with nearly the same temperature, interrupted only by tiny variations that later grew into galaxies and clusters. There is no sign of thinning space, no glow from a boundary, no preferred direction pointing toward an outer wall. The simplest interpretation is that the region we can observe is a limited sample of a much larger whole. The horizon belongs to our past light cone, not to the universe as a complete object. This does not tell us whether the whole is finite or infinite. It tells us only that the visible part is not known to be the whole. The distinction is easy to state and difficult to feel. Every image of deep space ends at the edge of a detector. Every map ends at a border. Every simulation occupies a box. The mind quietly converts those practical limits into physical limits. It imagines the last pixel as the last place. But the last photon a telescope can receive is not the last thing that exists. It is simply the last messenger that has reached us. The cosmic microwave background is sometimes described as the edge of the visible universe, but even this phrase needs care. The glow does not come from a shell that has always surrounded the Milky Way. The Milky Way did not yet exist when the light was released. The shell is created by the intersection of our present-past light cone with a particular moment in cosmic history, the moment when the early plasma became transparent. Look in one direction, and the microwave background comes from matter whose ancient light is arriving now. Look in the opposite direction, and it comes from entirely different matter at the same ancient stage. If an observer could instantly move to one of those distant regions, that observer would see a different microwave background sphere centered there. The surface of last scattering is therefore an apparent sphere, not a physical boundary wrapped around us. It resembles the surface of a cloud. From inside thick fog, a person sees only as far as the fog permits. The visible surface moves with the observer. There is more fog beyond it, but light from beyond has been scattered too many times to carry a clear image. In the early universe, the fog was made of charged particles. Photons bounced from free electrons again and again. The universe was not dark, it was intensely bright and hot. It was simply opaque. Light could not preserve a straight record of distant events. When electrons became bound into atoms, the fog lifted. The photons released into long free paths were stretched by cosmic expansion from visible and infrared wavelengths into microwaves. Their present temperature is only a few degrees above absolute zero. They form the oldest electromagnetic picture available. Older information may still exist in other forms. Neutrinos interact much more weakly with matter than photons do. In a standard picture of the early universe, a background of relic neutrinos separated from ordinary matter within the first seconds after the Big Bang. These particles should still fill space today, colder and harder to detect than the microwave background. No instrument has yet produced a direct image of that cosmic neutrino background, but its effects are woven into cosmological measurements. Gravitational waves could carry information from still earlier periods. Space-time itself can ripple, and those ripples can pass through matter that would trap light. A primordial background of gravitational waves might preserve traces of extraordinary processes in the earliest universe, including some models of inflation. Searches for their imprint continue, especially in the polarization pattern of the cosmic microwave background. So far, no confirmed primordial signal has been found. This reveals another important distinction. The electromagnetic edge is not necessarily the informational edge. Different messengers can travel through different conditions. A wall for photons may be transparent to neutrinos or gravitational waves. Even those messengers, however, do not let us observe an unlimited past. At sufficiently early times, known theories cease to provide a complete description. General relativity treats gravity as the geometry of space-time. Quantum theory governs particles and fields. Both work with extraordinary precision in their tested domains, but their combination becomes essential under the extreme densities and energies associated with the earliest moments. A complete, experimentally established theory of quantum gravity does not yet exist. The phrase "before the Big Bang" therefore carries several possible meanings. In the simplest classical extrapolation, time itself reaches a boundary where the equations become singular. In other models, the apparent beginning is replaced by a bounce, a transition, a quantum phase, or an earlier branch of cosmic history. None of these possibilities has been confirmed. The beginning of the observable expansion is not a place far away. It is a time in the past of every region. This is one of the hardest corrections to the ordinary picture. The Big Bang did not occur at one point in pre-existing space, with galaxies flying outward from the explosion. Space itself was once in a hotter, denser state. Every sufficiently large region visible today traces back toward that state. If the cosmic expansion could be run backward, the distance between unbound galaxies would shrink. Matter would become denser. Radiation would become hotter. But there would be no unique direction pointing toward the explosion center. From any galaxy, the broad pattern would look much the same. Raisins in rising dough are often used to illustrate this. As the dough expands, every raisin sees the others move away. No raisin on the inside of the dough is the center of the expansion. Once again, the analogy has limits. Dough expands into a kitchen, while the universe need not expand into anything. Still, it helps separate expansion from explosion. The same separation matters when asking what lies beyond the universe. An explosion has an outside because it occurs inside a larger arena. Cosmic expansion does not require such an arena. General relativity describes distances within space-time changing over time. It does not require space-time to be embedded in a higher dimensional room. The observable universe has a center in the modest, observer-dependent sense that every observation begins here. The universe as a whole has no known center. It may not have one at all. Now consider the spacecraft again. At the moment of departure, astronomers provide 3 maps. The first marks the particle horizon, the present boundary of everything whose signals have reached Earth since the early universe. The second marks the Hubble sphere, the distance at which cosmic recession, defined by the expansion rate, equals the speed of light. The third marks the cosmic event horizon, the boundary separating events that can still send signals to Earth from events that never can. These circles are often confused, but they describe different things. The Hubble sphere is not a true one-way barrier. Galaxies beyond it recede faster than light because the space between us and them expands. This does not violate special relativity, which forbids matter from locally passing through space faster than light. Cosmological recession is not an object racing past a nearby observer. It is the growth of distance across an extended spacetime. Light emitted by a galaxy beyond the Hubble sphere can sometimes still reach us. At first, the expanding space may carry the photon away even while it moves locally toward Earth. Later, as the expansion rate changes and the photon enters a region with a smaller recession speed, it can begin to reduce its distance and eventually arrive. Some of the galaxies visible today emitted the light we see while their recession speed was greater than the speed of light. So the surface where recession equals light speed is not automatically the limit of observation. The particle horizon answers a different question. What has been able to reach us by now? The event horizon asks, what emitted now will ever be able to reach us, even given unlimited future time? In the standard cosmological model, accelerated expansion creates an event horizon. Regions sufficiently distant today are being separated from us in such a way that a light signal they emit now will never cross the growing distance. The exact scale depends on the cosmological model and on the future behavior of dark energy, but in the usual model, the present proper distance to the event horizon is on the order of 16 billion light-years. This produces a result that initially seems impossible. The observable universe extends to a present distance of about 46 billion light-years, yet the event horizon is much closer. We can see many galaxies that we can never influence, and from which no message sent today will ever arrive. Their ancient light is already here. Their present light is not. A telescope can therefore show a galaxy that has already passed beyond future communication. The image is not false. It is a record from a time when the conditions of causal contact were different. The universe contains places that remain visible in their past while being unreachable in their present. This separation between seeing and reaching becomes clearer if the spacecraft sends a flashback toward Earth once every year. For a long time, each flash arrives later and redder than the one before it. The expansion of space stretches the wavelength. A blue photon may arrive as red light, then infrared, then radio. The signals weaken because their energy is reduced and because they spread across an ever larger area. If the spacecraft travels toward a sufficiently distant region, there may come a final flash whose light can still return. The traveler does not strike a barrier at that moment. No alarm sounds. Local physics remains ordinary. Stars, dust, and galaxies nearby behave as they did before. The significance of the crossing exists only in the global geometry of space-time. After that event, no later signal from the spacecraft can ever reach Earth. This is what a horizon means in relativity. It can be perfectly uneventful at the location where it is crossed and still determine the fate of every future message. A black hole event horizon works through a related causal principle, although the cosmological setting is different. Near a black hole, space-time is curved so strongly that all future directed paths inside the horizon lead deeper inward. A cosmic event horizon arises because the large-scale expansion prevents signals from bridging an ever-growing separation. Both are boundaries in causal structure rather than material surfaces. The traveler could continue to experience a local universe filled with galaxies even after Earth has lost all possibility of hearing from the spacecraft. From the traveler's new position, a new observable sphere would be centered there. Some regions hidden from Earth would become visible. Other regions, including parts of Earth's cosmic neighborhood, would move toward the traveler's own horizon. No observer possesses a complete view. This is not merely a limitation of telescopes. Building a larger mirror cannot recover a photon that never enters the past light cone. Waiting longer cannot reveal an event that has no causal path to us. Some ignorance is engineered into spacetime. The future of these horizons depends on what drives the accelerated expansion. Observations show that the expansion of the universe has accelerated during relatively recent cosmic history. The simplest explanation introduces a cosmological constant, a fixed energy density associated with empty space. In that model, acceleration continues indefinitely. Distant, unbound galaxies pass beyond future communication. Their light becomes increasingly redshifted, and the population of external galaxies that remains observable gradually dwindles until only the gravitationally bound local island is left. The cosmological constant fits a remarkable range of data, but the future is not observationally settled. Results from the Dark Energy Spectroscopic Instrument have strengthened hints that dark energy may evolve with time when its measurements are combined with several other cosmological datasets. Taken by themselves, the DESI measurements remain compatible with the standard cosmological model, and the hint is not a confirmed discovery. The completed 5-year survey is expected to test the question more sharply. If dark energy weakens or changes character, the event horizon could differ from the standard prediction or, in some models, fail to exist in the same form. If it becomes more extreme, the future could be stranger. Present measurements constrain these alternatives, but they do not turn the infinite future into an observed fact. This uncertainty matters. Statements about what will remain visible hundreds of billions of years from now are conditional statements. They describe what follows if the large-scale behavior measured today continues according to a particular model. Under the standard model, the long future is one of increasing isolation. The Milky Way and Andromeda belong to the same gravitationally bound neighborhood. Cosmic expansion does not steadily pull apart every system. Atoms remain intact. People do not expand. Planets remain in orbit. Galaxies inside bound groups can collide and merge. Expansion dominates mainly across sufficiently large distances where gravity has not tied matter together. The long-term orbit of the Milky Way and Andromeda is still uncertain. Simulations based on the latest Hubble and Gaia measurements give roughly even odds that the two galaxies will collide within the next 10 billion years. Other allowed paths include a wide encounter without a merger during that interval. If a close encounter occurs, their stars will rarely collide directly because the spaces between stars are enormous, but gravity can transform both galaxies. Over still longer times, the most tightly bound members of the local neighborhood may settle into a larger remnant. Beyond that bound region, other galaxy groups will recede farther and farther. Their visible light will stretch beyond optical wavelengths. Their images will fade. Eventually, in the distant future assumed by the cosmological constant model, observers inside the surviving gravitationally bound remnant of the local neighborhood may find no accessible evidence of the wider cosmic web through ordinary galactic light. They could inhabit a universe containing countless galaxies and yet see only one gravitationally bound island. The cosmic microwave background would also change. Expansion would continue to stretch its wavelengths and lower its temperature. It would become increasingly difficult to detect, eventually slipping beneath other backgrounds and practical limits. The great observational evidence for a hot, dense early universe could become hidden. A future civilization might look into an apparently static, dark cosmos and reasonably conclude that its galaxy is nearly everything. The history of expansion would be far harder to reconstruct. The edge of knowledge can therefore move inward even while the universe expands outward. Today is cosmologically fortunate. The microwave background remains measurable. Distant galaxies remain visible. Large surveys can trace the expansion history. The abundance of light elements preserves evidence of early nucleosynthesis. Several independent clues point toward a common story. Yet even now, the story reaches only as far as information permits. Astronomers sometimes use comoving coordinates to describe this changing universe. A comoving distance factors out the general expansion and assigns fixed coordinates to objects that simply follow the cosmic flow. Proper distance describes the separation at a particular cosmic time. Look-back time describes how long the observed light has traveled. Redshift describes how much its wavelength has been stretched. These quantities are related, but they are not interchangeable. A galaxy whose light has traveled for 10 billion years is not necessarily 10 billion light-years away now. Its present proper distance may be much greater. The galaxy may also have changed beyond recognition since the light began its journey. It may have merged, exhausted much of its gas, or fallen beyond the event horizon. There is no single everyday meaning of distance that survives unchanged across cosmology. This is why statements about the edge can sound contradictory. One number describes travel time. Another describes present separation. Another marks a causal limit. Another depends on a chosen model of the future. Without naming the quantity, a distance to the edge is almost meaningless. The spacecraft cannot simply aim for the particle horizon shown on today's map. That horizon is not a stationary destination. As time passes, the traveler's own past light cone grows. The matter associated with the horizon continues evolving and receding. The map is a statement about signals arriving here and now, not a border waiting at fixed coordinates. Trying to reach the observable edge is like trying to catch the end of a rainbow, except the analogy is deeper than perspective. The horizon is built from the relation between the observer, the light, and cosmic history. Move the observer, and the horizon changes. Even an immortal traveler moving arbitrarily close to the speed of light could not visit every region visible from Earth today. Much of the observable universe is already outside the region humanity can ever influence under the standard expansion history. The reachable universe is smaller than the visible universe. Humanity can receive ancient stories from places to which no reply can ever be delivered. The next map given to the imaginary traveler cannot be drawn as a simple circle. It concerns the geometry of the universe itself. Geometry is usually introduced through shapes on a flat surface. Parallel lines remain the same distance apart. The angles of a triangle add to 180 degrees. The circumference of a circle equals pi times its diameter. These rules feel inevitable because they describe small regions of everyday space extremely well. But they are not the only possible rules. On the surface of a sphere, lines that begin parallel can eventually meet. A triangle can have 3 right angles. Draw one line from the North Pole to the equator, follow the equator for a quarter of Earth's circumference, and return to the pole along another line of longitude. Each corner can measure 90 degrees, giving a total of 270. A saddle-shaped surface behaves in the opposite way. Lines can separate more rapidly than they would on a flat plane, and the angles of a triangle can add to less than 180 degrees. These two-dimensional surfaces help illustrate curvature, though cosmic space has 3 spatial dimensions. General relativity allows the large-scale geometry of space to be positively curved, negatively curved, or spatially flat. Positive curvature is often compared with a sphere. Negative curvature is compared with a saddle. Flat geometry follows the familiar Euclidean rules. The comparisons are useful, but no external dimension is required for the curvature to exist. Creatures confined to a surface could determine its geometry by measurements made entirely within the surface. In the same way, astronomers can test cosmic curvature without seeing the universe from outside. One method uses objects or patterns whose physical scale can be inferred. If the universe is curved, the apparent angular size of a known scale changes. Light rays converge or diverge differently as they travel through the geometry. The early universe supplied an especially valuable standard scale. Before atoms formed, ordinary matter and radiation behaved as a hot plasma. Gravity compressed over dense regions, while radiation pressure resisted the compression, producing acoustic waves. The maximum distance those waves could travel before the plasma became transparent left a characteristic imprint in the cosmic microwave background. Astronomers know the physical size of this sound horizon from the cosmological model and compare it with the angle it occupies on the sky. The result, strengthened by other measurements such as baryon acoustic oscillations, is that the observable universe is extremely close to spatially flat. This is an extraordinary result. Across tens of billions of light years, the geometry appears to follow flat space rules to the precision current observations can test. It does not prove that the universe is exactly flat. A tiny portion of a very large sphere also appears flat. A person standing in a field does not detect Earth's curvature by looking at a few meters of ground. If cosmic space has slight positive or negative curvature on a scale far larger than the observable universe, the visible region could look nearly Euclidean. There is another correction that is even more important. Flat does not automatically mean infinite. Local geometry and global topology are different properties. Geometry describes measurements in a neighborhood, distances, angles, and curvature. Topology describes how the whole space is connected. A sheet of paper and the surface of a cylinder are both locally flat. An ant walking on either surface finds ordinary Euclidean geometry in a small region. Yet their global structures differ. On the paper, a path in one direction can continue until it reaches an edge. On an ideal cylinder, a path around the curved direction returns to its starting point without encountering an edge. The cylinder appears curved when viewed from outside, but its intrinsic surface curvature is 0. It was formed by identifying 2 opposite edges of a flat sheet. No stretching was required. Now identify another pair of directions. A flat video game map can be programmed so that a character leaving the right side reappears on the left, while leaving the top causes reappearance at the bottom. The map has finite area, no boundary, and flat local geometry. Mathematically, this produces a torus, though its intrinsic structure need not resemble the familiar donut shape embedded in three-dimensional space. A three-dimensional version can be imagined from a room whose opposite faces are identified. Travel through the wall ahead and re-enter through the wall behind. Move through the ceiling and return through the floor. Move through the left wall and return through the right. Locally, the room is perfectly ordinary and flat. Globally, space is finite and has no edge. This is called a three-torus topology. The universe could, in principle, have a compact flat topology of this kind, or one of several related forms. It could be finite even if its spatial curvature is exactly zero. Conversely, some curved spaces can be infinite. The statement that a flat universe must extend forever is therefore too strong. Curvature measurements alone cannot decide the total size. To learn the topology, astronomers look for repeated patterns. If space wraps around on itself and is smaller than the observable region, light from the same galaxy or the same patch of the early universe could reach us along multiple paths. We might see repeated images of cosmic structures in different directions and at different apparent ages. The cosmic microwave background provides a particularly clean test. A compact universe could cause the spherical surface of last scattering to intersect copies of itself. The intersections would appear as matching circles in the microwave sky, with related temperature and polarization patterns. Searches have found no convincing evidence of such matched circles. Planck measurements place strong limits on several simple compact topologies. In particular, they rule out a cubic three-torus whose fundamental scale is substantially smaller than the diameter of the last scattering surface. But failure to find repetition does not prove that space is infinite. The repeating scale may simply be larger than the region we can observe. A room can look endless to an ant if the opposite walls lie beyond every distance it can explore. The traveler's geometric map is therefore incomplete. Observations say that the visible universe is very nearly flat and show no detected wraparound on scales small enough to leave clear repeated patterns. They do not reveal whether space continues forever or closes on itself beyond the horizon. Both possibilities remain open. If space is infinite, the traveler never reaches a final boundary. There is always another location ahead. If space is finite and multiply connected, the traveler may eventually return from another direction, though cosmic expansion and the event horizon may prevent the full circuit in practice. If space has slight positive curvature and a closed topology, a sufficiently long geodesic might also circle the cosmos, much as a great circle route eventually circles Earth. None of these cases requires an edge. A finite universe without a boundary sounds paradoxical only because finite objects in ordinary life are embedded in larger spaces. The surface of Earth has finite area, but no line where the surface stops. A ship can sail around it indefinitely. The surface has no special point labeled the end. Cosmic space may possess the same basic quality in three dimensions, a finite volume with no outer wall. The question, what is outside it, would then resemble what is north of the North Pole. The grammar is valid, but the geometry does not supply the requested direction. That comparison is useful only when stated carefully. A person can leave Earth's surface by moving upward because the surface is embedded in a larger three-dimensional space. A closed universe need not be embedded in a higher spatial dimension that a traveler could enter. The absence of an outside is not a locked door. It is the absence of the proposed location from the physical geometry. The spacecraft cannot turn away from all three dimensions of space and move into a fourth merely because imagination can name one. Mathematics permits higher dimensions, and some physical theories use them. But a higher dimensional model is not evidence for a surrounding room, and even an embedding space would not automatically be accessible or physically equivalent to an outside in the everyday sense. The global shape of the universe remains one of the places where observation reaches a real limit. We can measure the geometry of the visible patch. We can search for topology repeated within that patch. We cannot stand beyond the hole and look back at its silhouette. Still, it is worth asking what a literal boundary would mean. Suppose the spacecraft eventually finds a place where space ends. Ahead lies no distance, no direction, and no possible location. The traveler cannot move farther because farther has ceased to exist. This boundary would not be an ordinary wall. A wall occupies space and has another side. It has thickness, atoms, fields, and a location relative to other things. A boundary of space would instead be a termination of the set of possible positions. Physics can describe systems with boundaries. A wave on a string behaves differently if the end is fixed than if it is free. A field inside a box must satisfy conditions at the walls. In cosmology, however, introducing a genuine edge would require boundary conditions for gravity, matter, and quantum fields. Why does the boundary have those conditions? What determines its shape? Why is it located there rather than elsewhere? What happens to conservation laws near it? Such a proposal is not logically impossible simply because it raises questions. But it adds structure that observations do not currently demand. The standard large-scale models use spatial slices without ordinary edges. A boundary can also appear in a coordinate description without being physically real. Earth maps provide a familiar example. A rectangular world map has left and right edges, yet Earth's surface does not. The map must cut the sphere somewhere in order to lay it flat. The chosen seam belongs to the coordinates, not to the planet. Space-time coordinates can create similar illusions. A formula may become infinite or undefined at a location even though a better coordinate system passes through it smoothly. The event horizon of a non-rotating black hole produced such confusion in early coordinate descriptions. The apparent singularity at the horizon was not a destructive physical surface. The true singularity, according to classical relativity, lies deeper within. Cosmology requires the same discipline. A limit in a chart is not automatically the end of reality. There are mathematical spacetimes with boundaries, singularities, or incomplete paths. There are speculative models in which our observable region is a brane within a higher dimensional setting. There are models in which bubble universes form within an inflating background. There are proposals involving quantum creation, tunneling, cyclic histories, and transitions between phases of spacetime. These ideas do not all mean the same thing, and none gives permission to replace uncertainty with a picture of a glowing membrane. The most influential reason cosmologists consider regions far beyond our horizon is inflation. The observable universe has several properties that demand explanation. The microwave background has nearly the same temperature in widely separated directions. Yet in a simple non-inflationary expansion history, many of those regions would not have had enough time to exchange light or heat before the microwave background formed. This is the horizon problem. The visible universe is also remarkably close to spatially flat. In ordinary decelerating expansion, even a tiny early departure from flatness would grow in relative importance. Achieving the observed near flatness would require an extraordinarily precise initial condition. This is the flatness problem. Inflation proposes that the early universe underwent a brief period of extremely rapid accelerated expansion. A region small enough to become smooth and causally connected was stretched to enormous size. Its curvature was diluted, much as a small patch on an inflating balloon appears flatter as the balloon grows. Quantum fluctuations were stretched to cosmic scales, and became the seeds from which later structure developed. Several important observations agree with broad inflationary expectations. The primordial fluctuations are close to scale invariant, nearly Gaussian, and predominantly adiabatic. The universe is close to flat. The microwave background contains a pattern of correlations consistent with an early mechanism that placed regions in causal contact. But inflation is not a single fully confirmed model. It is a family of mechanisms. Different fields and potentials can produce similar observable outcomes. Some once popular versions are disfavored by data. No primordial gravitational wave signal has yet provided the dramatic direct evidence that certain models predict. It is therefore more accurate to say that inflation is a leading framework with substantial indirect support, not an observed event filmed by a telescope. If inflation occurred for long enough, the total region produced could be vastly larger than the observable universe. Our horizon would enclose only a tiny fraction of an expanded domain. Beyond it, space might continue with broadly similar physical conditions for distances beyond any conceivable measurement. Some models carry the idea further. Inflation may end in one region while continuing elsewhere. Quantum fluctuations can keep portions of the background in the inflating state, while local pockets exit inflation and evolve into hot, expanding regions. This process is known as eternal inflation. In that picture, what is casually called the universe may be one pocket among many. Other pockets could remain permanently causally disconnected. Depending on the underlying theory, they might share our physical laws or settle into different low-energy states with different constants and particle properties. The image of bubbles floating in a larger space is convenient and dangerous. The background is not necessarily ordinary space with bubbles moving through it like soap spheres in air. The geometry is dynamical, and the separation between pockets can expand so rapidly that communication is impossible. No spacecraft could leave our pocket, cross a calm interuniversal void, and enter the next. In many eternal inflation models, the intervening geometry prevents such a journey in principle. Eternal inflation also creates deep theoretical problems. If every allowed kind of pocket occurs infinitely many times, probabilities become difficult to define. Calculating the relative likelihood of observations requires a way to regulate infinities, known as the measure problem. Different procedures can give different answers. Other pocket universes have not been observed. Researchers have searched the microwave background for possible traces of collisions between bubbles, but no accepted detection has emerged. The multiverse may be a consequence of some theories, a clue to otherwise puzzling features, or a sign that the theories are being extended beyond the domain where they can be tested. Science has not settled the issue. This uncertainty should not weaken the central answer. Even without eternal inflation, the visible horizon is not expected to be an outer wall. The simplest cosmological models already place more space and matter beyond it. Inflation changes the possible scale of that unseen continuation. It suggests that the portion hidden from us may be not merely somewhat larger, but stupendously larger. A tiny coin placed on an endless plane and a tiny coin placed on a planet a trillion times wider than the coin would experience nearly the same local flatness. From the coin's surface alone, the difference might be impossible to determine. Our observable universe could occupy an analogous role, immense by every human standard, yet too small to reveal the global form of the whole. The traveler would not recognize the boundary of our observable patch by finding different laws or a change in texture. The boundary is not painted onto space. It is defined by which signals reach a chosen event. Crossing the location that Earth presently assigns to its particle horizon would not place the traveler outside the universe. It would place the traveler in a region whose ancient history has not had time to become visible from Earth. From there, the traveler would see another sky, The cosmic microwave background would again form a sphere around the new position. The distribution of galaxies would extend in new directions. Earth's observable map would appear provincial, one overlapping window among countless possible windows. The universe does not grant any observer the master map. What, then, should be expected in the unseen regions immediately beyond our horizon? The cautious answer is more of the same, at least on large scales. This expectation comes from the cosmological principle. When viewed across sufficiently great distances, the universe is statistically homogeneous and isotropic. Homogeneous means that no large region is fundamentally privileged over another. Isotropic means that the broad pattern looks similar in every direction. The principle does not claim that every place is identical. Earth is not identical to intergalactic space. A galaxy cluster is not identical to a void. The cosmos contains dramatic local variation. But when observations average over scales of hundreds of millions of light years, the distribution becomes increasingly uniform. Galaxy surveys reveal a cosmic web of filaments, sheets, clusters, and vast underdense voids. No surveyed direction points toward a special outer zone. The microwave background is extraordinarily uniform across the sky. These observations support using the same large-scale physical description beyond the visible boundary, unless evidence suggests otherwise. A region just beyond the particle horizon is not expected to be metaphysically remote. Its separation from visibility may be slight. Light from there may need only a little more cosmic time to arrive, depending on the event and the expansion history. There is no reason for matter to end exactly where our present past light cone ends. This is similar to standing at night beside an unlit road. The range of a lamp creates a circle of visibility. The darkness begins sharply from the observer's point of view, but the road does not change composition at the circle. Asphalt continues beyond the light. The analogy fails if stretched too far, because the cosmic limit cannot simply be overcome by installing a brighter lamp. Yet it captures the absence of a physical seam. Farther beyond the horizon, confidence weakens. The cosmological principle is inferred from the region available to observation. Extending it without limit is an assumption, though a well-motivated one. There could be structures or variations on scales larger than the visible universe. There could be gradual changes in fields, curvature, or physical conditions that no observation inside our patch can detect. A universe can look homogeneous within one window and differ beyond it. Inflation often suppresses such large variations, but different models allow different possibilities. Some predict an enormously smooth continuation. Others permit domains with altered conditions. No direct measurement selects among every global alternative. The phrase "beyond the observable universe" therefore covers a range of certainty. Just outside the horizon, continuation is strongly expected. Across unimaginably greater distances, theory plays a larger role and observation a smaller one. An infinite universe introduces a still stranger possibility. If space extends forever and matter continues with roughly uniform statistical properties, then there may be an unlimited number of galaxies, stars, planets, and regions resembling the one around us. Popular accounts sometimes leap from this to a dramatic conclusion. Somewhere, an exact copy of Earth must exist, together with exact copies of every person and every event. The conclusion is not as automatic as it sounds. To guarantee repetitions, several assumptions are needed. The universe must be spatially infinite or contain infinitely many suitable regions. The number of physically distinguishable states in a finite region must itself be finite, or at least limited in a relevant way. The distribution of states must explore the possibilities with suitable probabilities. Correlations or global constraints must not exclude the repeated configuration. Some approaches to quantum theory and gravitational entropy suggest a finite maximum amount of information in a bounded region with limited energy. Under those assumptions, an infinite statistically uniform cosmos would force approximate and perhaps exact repetitions. A finite set of possible arrangements placed into infinitely many boxes must repeat. But the argument depends on how physical states are counted, whether continuous quantities truly permit infinitely fine distinctions, and how the global universe is organized. It is better presented as a consequence of certain models than as an observed fact. Even an approximate duplicate would be staggeringly distant. Estimates sometimes produce numbers so enormous that writing all their digits would be meaningless. No signal could connect the regions. The duplicate would not offer a route to immortality, communication, or experiment. It would be a mathematical implication hidden beyond every possible horizon. The deeper lesson is not the existence of a cosmic twin. It is the difference between very large and infinite. A finite universe can be larger than any scale the mind can represent and still possess a total volume. An infinite universe has no total size at all. Adding another trillion light years does not bring a traveler closer to completion. There is no halfway point to infinity. This can be understood through ordinary counting. The sequence of whole numbers has no final member. No matter which number is reached, another follows. The numbers do not end at a mysterious wall beyond the largest value. The absence of an endpoint is part of their structure. An infinite spatial line behaves similarly. Every position has more positions beyond it. Asking what lies outside the line assumes an endpoint the line does not possess. Yet infinity in physical cosmology is not directly measured. Observations can establish lower bounds on scale and constrain curvature. They cannot inspect infinitely many regions. A claim that the universe is infinite always combines data with a global model. Scientists are sometimes comfortable with infinity because the equations permit it and because it simplifies the geometry. Others suspect that physical infinities signal an incomplete description. Neither preference decides the universe. If space is finite but vastly larger than the observable patch, every practical observation could look the same as it would in an infinite universe. The difference might never produce a measurable signal. This is one of the rare scientific questions for which improved technology may encounter a permanent ceiling. More sensitive telescopes can reveal fainter objects within the past light cone. Better surveys can constrain curvature and topology more tightly. New messengers can probe earlier epochs. But no instrument can collect data from a region that remains causally disconnected forever. The full size of the universe may not be merely unknown today. It may be unknowable in principle from our location. That possibility is not a failure of science. Science identifies the boundary between what evidence supports, what theory allows, and what no observation can decide. A precise statement of ignorance can contain more knowledge than a confident picture. The traveler, meanwhile, continues outward through the cosmic web. A filament appears ahead, carrying thousands of galaxies along a structure shaped by dark matter. Between filaments lies a void tens of millions of light years across. The void is not absolutely empty. Thin gas, dark matter, photons, neutrinos, and fields remain. Its galaxies are merely sparse. Beyond the void, another filament appears. Then another. If the large-scale pattern continues, the journey has no visual moment when the universe begins to run out. Average density does not steadily fall toward an edge. Galaxies are not arranged like trees thinning near the boundary of a forest. The forest analogy would imply a center and an exterior. Cosmology shows no such radial pattern. Any observer who waits long enough sees a different set of distant galaxies, but not because the whole has a preferred center. The observer's light cone selects a region from a larger space-time. The selection is personal to the event of observation. There may be no view from nowhere that gathers every region into a single present map. That last difficulty is not only about distance. It is also about the meaning of now. When someone asks what is at the edge of the universe, the question usually imagines the universe frozen at one universal present moment. Earth exists here now. A remote galaxy exists there now. Farther still, another region exists at the same now. Put all of them together, and the cosmos becomes a three-dimensional object whose outer boundary might be located. Relativity does not provide a single universal present shared by every observer. Events that are simultaneous in one frame of motion need not be simultaneous in another. For nearby objects moving slowly relative to one another, the difference is tiny and ordinary time works well. Across cosmological distances, the concept becomes more delicate. Cosmologists often define a useful cosmic time. In an idealized expanding universe, observers who move with the average cosmic flow can synchronize clocks according to the time elapsed since the hot early state. This allows statements such as the universe being about 13.8 billion years old. Cosmic time is extraordinarily useful, but it is part of a model adapted to the large-scale uniformity of the universe. It does not restore an absolute Newtonian present underlying all of physics. When astronomers observe a galaxy near the particle horizon, they see it in extreme youth. Asking what that galaxy is doing right now requires extending a chosen definition of simultaneity across a region from which present information cannot reach us. The answer is calculated, not observed. The galaxy may no longer exist in its ancient form. It may have merged repeatedly. Its stars may have enriched later generations with heavy elements. Its descendants may lie at a present distance far beyond the location assigned to the light we receive. The sky combines ancient observations with modeled dependent present distances. It is not a snapshot. This matters for the imagined wall. A wall at the edge would need to exist across some set of simultaneous events, but whose simultaneity defines its shape. In a dynamical space-time, a global boundary cannot always be treated like the wall of a box at one universal instant. The more carefully the question is made physical, the less it resembles an ordinary journey to a place. There is another way to see this. Imagine a graph with space along one direction and time along another. Light travels along diagonal paths, forming a cone of events that can influence an observer. The observer's past light cone contains every signal that can arrive now. The future light cone contains events the observer can influence later. Events outside both cones are separated in such a way that no light signal can connect them to the observer at that moment. They are not necessarily non-existent. They are causally elsewhere. The observable universe at a chosen time is related to the base of the past light cone. The event horizon concerns which distant world lines ever enter that cone in the future. These are four-dimensional relationships. Drawing a circle around a three-dimensional map hides the time structure that creates the circle. The edge is therefore less like the rim of a plate and more like the limit of a conversation. Some events have had time to speak to us. Others have not. Some can speak later. Others never can. The universe may contain an unlimited amount of reality outside the conversation. This also explains why moving faster cannot simply defeat every horizon. Special relativity permits massive objects to approach the speed of light, but not reach or exceed it locally. Even a photon follows the causal structure of space-time. If expansion shapes that structure so a destination lies outside the future light cone, no engine can force a path to it without violating the theory. Speculative ideas such as traversable wormholes or warp geometries are sometimes invoked. General relativity admits mathematical solutions with unusual properties, but producing and stabilizing them may require forms of energy or matter not known to exist in usable configurations. They do not currently offer an established route around cosmological causality. A wormhole, even if physically possible, would not automatically open into a region outside the universe. Its endpoints would still belong to a space-time or to a broader structure described by a theory. Calling one endpoint outside would not explain the geometry. The traveler cannot solve a conceptual error with a faster ship. The same caution applies to the phrase, "the universe is expanding faster than light." There is no single outer surface racing into a void. At sufficiently large separations, proper distance between comoving objects can increase faster than light. This is allowed because the objects are not locally overtaking light in their immediate neighborhoods. Expansion has no known leading edge. If the universe is infinite today, it may also have been spatially infinite at earlier times, even when it was far denser. Expansion does not necessarily mean a finite object becoming larger. An infinite line can be stretched so that every pair of marked points becomes farther apart, while the line remains infinite before and after. This fact overturns another common image. The early universe may have been small in the sense that the observable region was compressed into a much smaller volume. It does not follow that the entire universe was a tiny ball. If space is globally infinite, the hot early universe could also have been infinite, with every finite separation reduced. The phrase "the universe was once the size of a grapefruit" usually refers, at best, to the matter now contained within the observable universe. It does not establish the size of the whole. If space is finite, its total volume may indeed have been smaller, yet it still need not have occupied a surrounding emptiness. The scale factor describes internal distances. There was no first expanding frontier sweeping outward and converting nothing into space. This helps answer what lies just beyond the most distant visible matter. The answer is not a construction zone where space-time is being created. Expansion occurs throughout the large-scale geometry. Every unbound separation participates. Galaxies do not sit at the tips of an explosion. The cosmic web has no outermost strand known to physics. The observer-centered sphere can encourage the illusion of a center. Images often place Earth in the middle and the microwave background at the rim. Such diagrams are correct for our past light cone, but they are not overhead photographs of the entire universe. Replace Earth with any sufficiently typical galaxy, and a similar diagram can be drawn around it. The rim belongs to the diagram's question: what can arrive here now? It does not answer: where does existence stop? A more powerful telescope does not move the horizon outward in the way a stronger lamp illuminates a larger room. It can recover signals that were already arriving but too faint or too red to measure. It can distinguish galaxies that blended into the background. It can detect wavelengths hidden from human eyes. It can approach the practical limits set by nature. The James Webb Space Telescope, for example, observes infrared light from very distant galaxies. Their ultraviolet and visible radiation has been stretched into infrared wavelengths by expansion. Webb can study systems from the universe's first few hundred million years and reveal how rapidly early galaxies formed. When a new record for the most distant known galaxy is announced, the edge of the universe has not been reached. Astronomers have found a brighter or earlier object within the observable volume. There is likely an era before the first stars when no galaxies existed to be seen. Beyond the earliest galaxies in look-back time lies the cosmic dark ages, neutral gas, dark matter, radiation, and slowly growing density variations. Beyond that lies the microwave background. The sequence is an edge in time, not a thinning line of objects toward a spatial wall. Future radio observations may map neutral hydrogen from the dark ages through its 21-centimeter signal. Such measurements could reveal structure before starlight, fill a major gap in cosmic history, and test inflation and dark matter. they would still remain inside the causal limits of our region. Astronomers use several methods to infer the geometry and expansion that shape those limits. Standard candles are objects whose true luminosity can be estimated. Comparing true luminosity with apparent brightness gives a distance. Type 1, a supernovae, played a central role in discovering accelerated expansion. Standard rulers have a known physical scale. Baryon acoustic oscillations leave a preferred separation in the distribution of galaxies, inherited from sound waves in the early plasma. Measuring that scale across different redshifts traces the expansion history. Gravitational lensing reveals how mass bends light and helps map both ordinary and dark matter. Galaxy clustering shows how structure grew. The microwave background anchors the early universe. Combining these observations constrains the parameters that determine horizon distances. No single measurement alone produces the entire cosmological map. The conclusion emerges from consistency among many forms of evidence. That consistency is impressive but not perfect. Measurements of the present expansion rate have produced a persistent tension between values inferred from the early universe under the Standard Model and values measured using some local distance ladders. Surveys of recent cosmic history are testing whether dark energy remains constant. Researchers examine possible systematic errors as well as new physics. These open questions could refine estimates of future horizons. They do not currently suggest a nearby spatial edge. The visible universe is so large that even its lower dimensional analogies become misleading. The last scattering surface surrounds us at a comoving radius near 46 billion light-years. Its area is enormous, yet it is only a two-dimensional slice through the four-dimensional history accessible to us. Inside it are the world lines of matter across cosmic time. A galaxy survey maps not just position, but epoch. Nearby galaxies appear relatively recent. More distant galaxies appear younger. The farther layers are different because the universe evolved, not necessarily because location alone changes the laws. Suppose a survey finds that remote galaxies are smaller, more irregular, and more actively forming stars. It would be a mistake to conclude that the universe becomes primitive near its outer edge. Those galaxies are seen earlier in time. Their later descendants may be as mature as nearby galaxies, but their later light has not arrived. The observable sphere is onion-like only as a record of history. This distinction removes another imagined boundary. There is no final shell populated by the oldest galaxies, with nothing behind them. There are earlier phases behind them in look-back time, and likely more regions beyond them in space. The relation between those two directions can be difficult to express because looking outward is looking backward. The farthest visible distance and the earliest visible time appear in the same direction on the sky. A telescope points away from Earth spatially and toward the Big Bang temporally. At the microwave background, every line of sight reaches nearly the same early epoch. The image forms a sphere because all directions eventually intersect that epoch in our past light cone. Beyond the sphere spatially lies more early universe matter whose photons have not reached us. Before the sphere temporally lies the opaque plasma and whatever earlier physics occurred. The word beyond splits into two meanings at once. A careful cosmic map must therefore label its axis. Beyond in distance is not beyond in age. Outside our observable sphere is not before the Big Bang. The unobservable universe is not a region located on the far side of the microwave background as though the background were a painted curtain. Imagine two ancient photons arriving from opposite directions. They were emitted by matter now separated by a vast present distance. Trace their paths backward, and the paths diverge from Earth into the past. Continue into the early universe, and the geometry becomes denser and hotter. The photons do not meet at a distant outer wall. Their history belongs to different locations in an earlier cosmic slice. Inflation was introduced partly because those widely separated regions show temperatures too similar to explain easily without earlier causal contact. The smoothness of the apparent rim tells a story about conditions before the rim became transparent. The edge is full of evidence about what lies earlier, not evidence that nothing lies farther. Even the phrase, oldest light, needs one refinement. The individual microwave photons have traveled freely since recombination, but radiation existed before that. Their final scattering erased the directional memory of earlier paths. The surface is the last place where the photons interacted strongly enough for an image to form, not the moment light itself was created. A similar principle appears when looking at the sun. Visible photons reaching Earth were produced and absorbed many times in the solar interior before their last scattering near the photosphere. The visible surface is where the sun becomes transparent, not where the sun begins. The cosmic photosphere surrounds every observer. If a telescope could be placed 10 billion light-years away at the same cosmic time, its cosmic photosphere would overlap ours but not coincide with it. It could sample regions of the primordial plasma forever hidden from Earth. The universe contains more historical information than any one observer can collect. A civilization cannot combine observations from causally disconnected locations after the fact. Even if intelligence arises across the cosmos, accelerated expansion may prevent their records from ever being gathered into one archive. There may be truths about the global universe that no single physical system can store, because no causal network can reach every relevant region. The edge of the universe becomes, in this sense, an edge of possible evidence. Consider the finite possibilities more closely. A positively curved universe is often compared to the three-dimensional analog of a sphere's surface. The technical object is a three-sphere. Its volume can be finite, and every direction can continue without meeting a boundary. Geodesics can eventually return to their origin. If the spacecraft followed a straight enough path in such a static space, it might circumnavigate the universe. In a real expanding cosmos, the path and the scale change with time, so the practical result depends on the expansion history. A sufficiently rapid expansion could keep the traveler from completing the circuit. A compact flat universe offers a different kind of return. Instead of curvature bending the path, topology identifies distant directions. The traveler leaves one face of a fundamental domain and enters through an equivalent face, though there is no physical seam where the identification occurs. If the fundamental domain were smaller than the observable universe, the sky might contain multiple images of the same galaxy. Those images would not necessarily look identical. Light following different routes would take different amounts of time to arrive. One image might show the galaxy before a major merger and another after it. A civilization could, in principle, see ancient versions of its own region in the sky, though dust, evolution, motion, and the complexity of real topology would make recognition difficult. The microwave background avoids some of these complications because it comes from a single narrow epoch. Matching circles would preserve correlated patterns more clearly. The absence of detected matches tells us that any simple wraparound scale must be large enough to hide the repetitions. This gives a useful lower limit, not a final answer. There are many possible topologies, including asymmetric ones. A universe might wrap in one direction but extend far in others. It might have a compact hyperbolic topology. The orientations and sizes of the fundamental directions could complicate searches. Cosmic variance, the fact that only one realization of the large-scale sky is available, also limits certainty. We cannot make another universe and repeat the measurement. This is an unusual experimental situation. In a laboratory, many systems can be prepared under similar conditions. Cosmology has one observable cosmos and one past light cone. Researchers must extract general laws from a single historical object. The largest scales contain relatively few independent patterns. Random fluctuations can mimic anomalies or conceal real ones. Features such as unusual alignments or cold regions in the microwave background attract attention, but establishing that they require new global physics is difficult. The absence of a confirmed topology signal is therefore meaningful without being absolute. A finite universe can be much larger than its visible portion. If its circumference were hundreds or thousands of times the diameter of the observable universe, no repeated image could have reached us. Local measurements would be indistinguishable from infinity. The question of size then resembles measuring Earth while confined to a tiny, enclosed field. The ground appears flat. No path reaches a wraparound. Every experiment is compatible with a plane extending forever or with a planet whose curvature is too small to detect inside the field. Earth's explorers eventually crossed oceans and compared stars from different latitudes. Cosmological explorers cannot simply travel outside the observable patch and report back. The field's boundary recedes according to causal law. Curvature constraints may improve. Galaxy surveys can map baryon acoustic oscillations across larger volumes. Gravitational wave sources may become standard sirens for distance measurements. 21-centimeter cosmology could offer vast numbers of modes from early epochs. Better microwave polarization maps can test large-scale patterns. But even perfect measurement of zero curvature would not by itself establish infinite extent. Topology would remain. This is why the answer to "Is the universe finite?" is not identical to the answer to "Is the universe flat?" A common simplified branch, positive curvature, means finite, while flat or negative curvature means infinite, misses this distinction. The complete picture is richer. Positive curvature often supports finite closed models, though global identifications still matter. Zero curvature allows infinite Euclidean space or finite compact spaces. Negative curvature can be infinite or, with suitable identifications, finite and compact. Geometry does not dictate topology. There is elegance in this ambiguity. A traveler can measure every local angle and still fail to know whether a path eventually returns. The whole cannot always be inferred from the neighborhood. The universe may be globally simple, an endless three-dimensional Euclidean space. It may be a closed three-sphere. It may wrap through a topology too large to reveal itself. The visible evidence has not selected a final shape. None of the leading possibilities contains an ordinary border. A topology can also be non-orientable in mathematical examples, meaning that a traveler completing certain loops returns with orientation reversed. Whether such exotic cosmic forms are physically plausible is another question, but they demonstrate how limited the wall picture is. Space has more ways to be finite than a box. The box dominates intuition because it is easy to draw. A finite volume seems to demand 6 faces. Yet faces are properties of one topology, not of finitude itself. A circle is finite in length and has no endpoints. A sphere is finite in area and has no boundary line. A three-sphere can be finite in volume and have no boundary surface. Each step adds a dimension while preserving the central idea. The traveler does not need to leap off the circle or sphere. Those imagined external directions belong to an embedding used for visualization. Intrinsic inhabitants can move through every available direction without finding an edge. If the universe is a three-sphere, asking what lies outside may have no answer within the physical model. Mathematicians can embed some curved spaces in higher dimensional spaces, but the embedding is a representational tool. The higher space need not be physical. A map of Earth can be drawn on paper, but Earth does not physically reside inside the paper. Likewise, an equation can represent the universe within a larger mathematical framework without turning that framework into a place where rockets can fly. The absence of an outside does not mean the universe is surrounded by nothing. Nothing is often imagined as empty black space, but empty space is already something in physics. It has geometry. Quantum fields exist in it. It can expand. It can possess vacuum energy. True absence of space is not a dark room. A dark room has dimensions and locations. There is no distance from the universe to the absence of distance. The word nothing causes much of the confusion. When people picture what might be beyond the universe, they often see a limitless black background. But blackness is an appearance produced when light does not reach an eye or detector. It assumes a place where an observer could stand, a direction in which the observer could look, and time during which the observation could occur. A black void is not nothing. It is an empty region of space-time. Intergalactic voids are dark by ordinary standards, yet they contain physical fields, sparse particles, relic radiation, dark matter, and a geometry capable of carrying light. Even a perfect vacuum in quantum field theory is not a featureless absence. It is the lowest energy state of fields, with measurable consequences. To say there is no space outside a boundaryless universe is not to say a black substance surrounds it. It is to say that the spatial relation outside is not defined. Language resists this. A noun seems to demand a location. The universe must be somewhere. A beginning must happen at some time. A finite thing must be contained. But grammar was shaped by objects within the universe, not by the universe as a whole. Physics often progresses by discovering where ordinary categories fail. Before relativity, time appeared universal. Before quantum mechanics, particles seemed to possess definite classical properties at every moment. Before curved geometry, parallel lines seemed incapable of meeting. The failure of intuition is not evidence of nonsense. It is evidence that intuition was trained on a narrow range of scales. The cosmic edge lies far outside that training range. One response is to imagine a hierarchy. Our universe sits inside a larger universe, which sits inside another, and so on. This can postpone the question, but not answer it. The larger arena acquires the same problem. What contains it? Another response is to declare that the universe emerged from nothing. In cosmology, however, nothing in a model often means a quantum state, an absence of classical space-time, a boundary condition, or a particular mathematical proposal. These meanings are not interchangeable with philosophical nothingness. A quantum vacuum is not nothing. A law permitting a universe to nucleate is not nothing. A wave function is not nothing. The ultimate origin question remains open. That openness belongs in a truthful account of the edge. It is possible to explain what current cosmology says without pretending that every level of reality has been solved. We know the observable region has a finite horizon. We know space on large scales is close to flat. We know no compact topology has been detected within the scales tested. We know accelerated expansion effects which regions can communicate. We do not know the full spatial extent, the global topology, the exact nature and future behavior of dark energy, or the complete physics of the earliest moment. The unknowns are specific rather than shapeless. A good map labels unexplored territory instead of filling it with monsters. There was a time when the Milky Way seemed to be the whole stellar universe. The faint spiral nebulae were debated, nearby clouds or distant island universes. Measurements eventually established that many were separate galaxies far beyond the Milky Way. Later, galaxies were found in clusters and superclusters. Surveys revealed filaments and voids. Each enlargement transformed the meaning of the universe in ordinary speech. The lesson is tempting. Every horizon will eventually fall, so the present cosmic horizon must also be temporary. But history does not guarantee that every boundary is technological. The edge of the Milky Way could be crossed because it is made of distance. The particle and event horizons are made of causal structure. No larger telescope changes the age of the universe. No longer voyage lets a signal return from outside a future light cone. Human knowledge expanded past former practical horizons, yet cosmology includes possible horizons in principle. The distinction can feel severe, but it also gives the visible universe a precise character. The observable cosmos is not an arbitrary sample chosen by limited engineering. It is the maximal region that has participated in our causal history so far, subject to the messengers available. Its scale is almost impossible to picture. Light circles Earth more than 7 times in 1 second. It reaches the Moon in a little over a second and the Sun in about 8 minutes. It takes years to reach nearby stars, tens of thousands of years to cross much of the Milky Way, millions of years to cross the distances between neighboring large galaxies, and billions of years to bring news from the early cosmic web. The present particle horizon lies about 46 billion light-years away in every direction in comoving terms. The volume enclosed is roughly 4 times 10 to the 32 cubic light-years, a number so large that naming it contributes little to intuition. Yet if inflation expanded a much larger domain, this entire region may be a microscopic fraction of the whole. Size does not bring us closer to an edge if no edge exists. The spacecraft in the thought experiment has now traveled beyond every recognizable landmark in Earth's maps. Its onboard clocks measure a finite journey. Its local instruments still find space-time. A hydrogen atom behaves according to the same spectral rules. Gravity shapes nearby systems. The microwave sky is shifted because the traveler occupies another event, but it does not vanish. Ahead is not a blank panel marked unknown. Ahead is a sequence of possible events. If the traveler continues through an infinite universe, there is no final destination. If space wraps, the journey may reveal repetition. If acceleration dominates, increasing portions become unreachable even as local travel continues. If the larger structure varies beyond our patch, the traveler might encounter conditions no earthbound theory predicted, though no report may return. The most dramatic possibilities are also the least testable from here. This is why cosmology must balance imagination with restraint. Mathematical consistency is necessary, but not sufficient. A model can be beautiful and still fail to describe nature. A possibility can be fascinating and still lack evidence. The boundary between established result and speculation should remain visible even when the subject itself concerns invisible boundaries. The modern answer was not reached in a single step. For much of recorded history, the heavens appeared as a dome. Stars seemed attached to a distant sphere surrounding Earth. The sphere had a natural edge because it was itself a boundary between the human world and whatever lay beyond. The invention of the telescope did not immediately remove the sphere, but it began to weaken it. More stars appeared wherever instruments looked. The Milky Way dissolved into innumerable points. The sky became deeper. Isaac Newton imagined a vast, perhaps infinite space governed by universal gravity. An infinite static distribution of stars created its own problems. Why did gravity not pull everything together? Why was the night sky dark if stars extended forever in every direction? The darkness of night, known through Olbers' paradox, became a clue. In an eternal, static, infinite universe filled uniformly with stars, every line of sight should eventually end on a stellar surface, making the sky bright. The real night is dark because the universe has a finite age, stars have finite lifetimes, and cosmic expansion redshifts distant radiation. Darkness does not mark an outer wall. It records cosmic history. When Einstein applied general relativity to the universe, the equations naturally permitted a changing cosmos. He initially preferred a static model, and introduced the cosmological constant to support it. Soon, solutions found by Alexander Friedman and Georges Lemaitre described expanding or contracting space. Edwin Hubble's observations helped establish that distant galaxies are generally redshifted in proportion to distance. The universe was not a fixed stage. Its large-scale geometry evolved. This changed the edge question. In a static cosmos, one might ask how far space extends at a single eternal time. In an expanding cosmos, horizons depend on the entire history of the scale factor. The distance light can cross is determined by how rapidly space grows during the journey. The discovery of the cosmic microwave background in the 1960s supplied evidence for a hot early state. Later satellites measured its spectrum and tiny anisotropies with increasing precision. COBE established the near-perfect blackbody spectrum and detected primordial temperature variations. WMAP refined cosmological parameters. Planck mapped temperature and polarization across the full sky with extraordinary detail. Each mission looked toward the apparent rim and found not a boundary, but an earlier chapter. Supernova observations near the end of the 20th century then showed that expansion is accelerating. The future horizon became as important as the past one. A universe once imagined as gradually revealing more and more of itself may instead hide most external galaxies forever. The history forms a pattern. Better observations repeatedly replace a material edge with a relation among space, time, and light. The stellar sphere became a deep galaxy field. The last galaxies became the Dark Ages. The Dark Ages led to the microwave background. The microwave background became a transparency surface rather than a beginning. Beyond electromagnetic visibility lie other potential messengers and unknown early physics. At no stage did a telescope photograph the outside. This does not mean the search has failed. The search changed the meaning of the target. The same transformation occurred with Earth's horizon. A distant sailor did not find a cliff where sea ended. The horizon became evidence for geometry. In cosmology, the farthest light likewise teaches the shape and history of space-time. The analogy differs in one essential respect. Sailors could meet, combine maps, and circumnavigate Earth. Cosmic observers separated beyond event horizons cannot assemble a common atlas. The global voyage may be physically impossible. Still, the intellectual method is similar. Do not mistake the limit of a viewpoint for the limit of the world. The universe has repeatedly proved larger than the category used to contain it. A planet became one world among others. The solar system became one system among stars. The Milky Way became one galaxy among many. The observable universe may be one causal patch in a much greater reality. The next step, however, has not been observed in the same way as the earlier steps. Other planets can be detected. Other galaxies can be imaged. Other causal patches beyond the horizon cannot send evidence to us by definition. The analogy must stop where testability stops. This is the quiet tension at the center of modern cosmology. The equations invite global pictures. The data arrive through one local light cone. Researchers handle that tension by building models whose observable consequences can be tested. Inflation, for example, is not assessed by visiting the region beyond the horizon. It is assessed through the statistics of primordial fluctuations, curvature, polarization, and structure. Compact topology is tested through repeated patterns. Dark energy models are tested through distances and growth. A theory about the unseen earns credibility through what it predicts in the seen. The edge itself may never be reached, but its possible forms cast shadows into observable data. Positive curvature would alter angular scales. A small compact topology would repeat patterns. Bubble collisions might disturb the microwave background. Primordial gravitational waves could support particular early universe energies. Evolving dark energy would change expansion and structure growth. So far, the broad picture remains close to a simple model: nearly flat large-scale space, cold dark matter, ordinary matter, radiation, and a dark energy component resembling a cosmological constant. The model is not a complete theory of everything. It is a remarkably successful description of the observable cosmos. Within that model, the universe has no known spatial edge. It has a particle horizon, an event horizon, a surface of last scattering, and a limit where current theory becomes incomplete. Those are real boundaries of knowledge and influence. None is a wall where space ends. Higher dimensions offer one of the most persistent versions of an outside. In some theories inspired by string theory, the familiar universe may be associated with a three-dimensional brain embedded in a higher dimensional bulk. Ordinary particles and forces might be confined to the brain, while gravity can interact with extra dimensions. Cosmological evolution could involve brain motion or collisions. These ideas show that physics can meaningfully discuss a larger structure containing our observed spacetime, but they do not establish that such a structure exists. Extra dimensions have not been directly detected, and many versions are difficult to test. Even if a bulk exists, it would not resemble the black emptiness outside a bubble. It would possess its own geometry, fields, and laws. It would be part of a broader physical universe under a wider definition. The word universe shifts again. It can mean the observable universe, the connected space-time produced by our cosmic history, or the totality of all physical reality. A claim about an outside may become true or false depending on which meaning is chosen. There is certainly an outside to the observable universe, regions not visible from Earth now. There may be regions outside our causal patch, events that never exchange signals with us. There could be other domains outside the space-time region informally called our universe in some multiverse models. But there cannot be a physical outside to the universe when universe is defined as all physical reality. Anything discovered there would join the definition. This is not wordplay used to avoid the question. It separates an observational boundary from a logical one. A continent can lie outside a map because the map represents only part of Earth. Nothing physical lies outside all physical reality by definition. The meaningful question becomes whether the domain currently called our universe is only part of a larger structure. Science allows that possibility. It does not yet possess decisive evidence. Another proposal replaces the outer edge with a boundary in the laws of time. The no-boundary idea in quantum cosmology, associated with James Hartle and Stephen Hawking, uses a geometry in which the earliest region does not have an ordinary temporal boundary. Time may behave more like a spatial direction near the beginning, smoothing away a sharp first instant. The usual analogy is Earth's surface. Latitude decreases toward the South Pole, but the pole is not an edge requiring a location farther south. Likewise, a quantum cosmology might be finite in imaginary time without a singular beginning boundary. This is a mathematical proposal, not a confirmed description. It demonstrates again that finite does not require an edge. The lesson can apply to time as well as space. Other models propose a bounce. A contracting phase reaches high density and transitions into expansion. Cyclic models repeat large-scale phases. Loop quantum cosmology, ekpyrotic scenarios, and other approaches construct different mechanisms. Each faces theoretical and observational tests. If one were correct, the hot Big Bang would not be the absolute beginning. It would be a transition. Yet none of these models gives the traveler a destination called the edge. They move the unanswered question into deeper structure. Perhaps spacetime is emergent rather than fundamental. Some approaches to quantum gravity suggest that geometry arises from quantum information, entanglement, networks, or more basic degrees of freedom. If so, asking what lies outside space may resemble asking what lies north of a direction that has not yet emerged. At sufficiently fundamental scales, even the concepts of location and distance may lose their ordinary meaning. This possibility is difficult to visualize because every visualization already uses space. A network drawn on paper appears embedded in a room, even if the mathematical relations do not require that room. The mind supplies an external stage automatically. The edge question may ultimately be answered not by identifying a remote object, but by explaining why space exists as a useful concept at all. That does not make the large-scale questions obsolete. Emergent space could still possess global topology, curvature, and horizons. A fluid is made of molecules, yet coastlines and waves remain real at larger scales. Different levels of description answer different forms of the question. At the level of present cosmology, the traveler follows geodesics through an expanding space-time. At the level of quantum gravity, the traveler and the path may be patterns in a deeper system. At neither level is an ordinary brick wall expected. The desire for a wall comes partly from the need for closure. A wall would settle the matter. It would provide a final object to photograph, measure, and perhaps touch. Beyond it, one last mystery could be named. A boundaryless universe denies that closure. It permits endless continuation or finite return. It replaces the last object with a structure. There is no final galaxy holding a sign. Galaxies are local arrangements of matter. Their distribution can become sparse or dense, but space does not depend on a last galaxy to continue. Empty regions remain regions. A traveler can pass beyond all nearby luminous matter without leaving the universe. Nor is there a temperature at which space stops. The cosmic background can cool arbitrarily close to absolute zero while geometry remains. Darkness, cold, and emptiness are conditions within the universe, not evidence of its exterior. A true edge would need a reason grounded in the laws. Current observations offer none. The cleanest working picture is therefore modest. The observable universe is finite. The universe appears to continue beyond it, and may be vastly larger. Spatial curvature is extremely close to flat. Global topology is unknown, and no ordinary boundary has been detected or required. Every stronger statement needs a condition. If the simplest infinite topology is correct, space extends without end. If a compact topology is correct, space is finite and wraps without an edge. If eternal inflation is correct, our region may be one among many causally isolated domains. If dark energy remains a cosmological constant, much of the visible universe will fade permanently beyond future communication. If new physics changes the expansion, the future causal map may change. The edge question does not have one dramatic answer because it contains several scientific questions folded together. Return once more to the spacecraft, now not as a vehicle expected to succeed, but as a way to test each meaning. It aims first for the most distant galaxy currently visible. That target is not at the particle horizon. Galaxies formed long after the microwave background was released, so even the earliest known galaxies occupy a later layer of the past light cone. The traveler must choose whether to head toward the ancient position from which the observed photons departed or toward the calculated present position of the galaxy's descendants. The ancient position is no longer occupied by the same matter in the same state. The present position may be causally unreachable. A picture in a telescope is not an address that remains fixed for delivery. The spacecraft next aims for the surface of last scattering. Again, there is no object waiting at the marked radius. The matter responsible for the microwave photons has evolved for more than 13 billion years. It may now reside in galaxies, stars, gas, black holes, or voids at far greater separation. The surface exists as a set of emission events in the past, not as a shell in the present. The traveler then aims for the event horizon. This target also fails to behave like a destination. The horizon is observer-dependent and time-dependent. It describes which future signals can reach a chosen world line. Change the traveler's motion and the relevant causal region changes. There is no universal painted sphere. Finally, the spacecraft aims for the edge of space itself. No observation supplies coordinates. If the universe is infinite, none exist. If it is compact, the course may wrap. If it has a global form larger than the visible patch, the route cannot be planned from available data. Each attempted destination dissolves for a different reason. The most distant visible object is a past event. The microwave background is a transparency surface. The event horizon is a causal boundary. The global edge may not exist. This layered failure is the real answer, and it is more interesting than a wall. It shows that the universe is not assembled from a static stack of shells. It is a space-time history. Light arriving at one event carries partial records of other events. Geometry decides which records can meet. The traveler can still explore nearby stars, the Milky Way, the local group, and perhaps farther structures remain physical destinations. The impossible total journey does not make local journeys meaningless. It defines their domain. There is a maximum region that signals launched from Earth now can ever influence under a chosen cosmological model. This future reach is much smaller than the present observable universe. Some estimates place the currently reachable comoving radius at only a fraction of the particle horizon radius, even for signals moving at light speed. The exact number depends on the expansion history and on what is meant by reach, but the qualitative fact is firm in an eternally accelerating model. Most galaxies now visible are already beyond any message humanity sends today. Their light enters our telescopes as a one-way inheritance. This can be viewed as loss, but it also gives cosmic observation an unusual intimacy. A photon may travel for 10 billion years, pass through intergalactic gas, have its path bent by foreground gravity, and end in a detector for a fraction of a second. It delivers information from a source that can never know it was received. The universe is full of messages without replies. As expansion continues, a distant galaxy's successive signals arrive with increasing delay. Each wave crest is stretched farther from the next. The source appears to slow and fade. There is no observed moment when it crashes through a border. Its story becomes asymptotically harder to read. The final visible image is not a sharp farewell. It is a redshift towards silence. Nearer-bound systems remain. Stars continue to form for a long time, though usable gas declines. Stellar remnants accumulate. Black holes persist on timescales beyond ordinary comprehension. The far future predicted by the Standard Model is shaped less by a spatial edge than by energy, entropy, and isolation. The universe may become darker without becoming smaller. Its accessible islands may become fewer while total space continues expanding. An observer in that future could still ask what lies at the edge. The available evidence would be poorer. The answer might be reconstructed through relics inside the local island, or it might be lost. Knowledge itself has a cosmological era. This gives present observations a kind of urgency without requiring drama. The broad cosmic web is visible now. The microwave background is measurable now. Distant supernovae and galaxies preserve the expansion history now. Civilizations, if they exist much later, may not receive the same archive. The edge is not only where information fails to arrive. It is where information that once arrived eventually fades from practical recovery. No physical law guarantees that the universe remains equally knowable at all times. The traveler's last signal, sent just before crossing Earth's event horizon, would not contain news of a wall. It would contain ordinary measurements, local temperature, nearby galaxies, the frequency of a clock. The strangeness would appear only when no later signal followed. From Earth, the silence could never prove that the traveler crossed a horizon rather than stopped transmitting. Horizons are inferred from the model of space-time, not marked by a final photograph. From the spacecraft, Earth might likewise fade. Each side would continue into a future the other could not witness. Causal separation creates multiple histories that coexist without meeting again. If eternal inflation produces separate pockets, this separation becomes even more severe. If compact topology returns paths, it can become less intuitive. If quantum gravity alters causal structure, the deepest story may differ. Yet within every tested regime, information remains the key. An edge that cannot send a signal is scientifically different from an edge that does not exist, but observation from one side can struggle to distinguish them. This is why cosmologists search for indirect imprints. A hidden region may affect initial conditions. A topology may repeat patterns. An early phase may alter correlations. The unseen becomes scientific when it changes the seen in a calculable way. Where no imprint is possible even in principle, the claim moves toward metaphysics. The line between cosmology and metaphysics is not fixed by distance. It is fixed by testable consequence. Future observations may narrow the possibilities without producing a photograph of an edge. A more complete map of galaxy positions and motions can test whether large-scale geometry remains consistent with flatness. Large samples of supernovae and other distance indicators can trace the recent expansion. Gravitational lensing can reveal how structure responds to dark energy. Standard sirens from merging neutron stars and black holes may provide an independent distance scale. Microwave observatories can improve polarization measurements and search for primordial gravitational waves. A confirmed primordial tensor pattern would open a view toward inflationary energies, though interpreting it would still require care. Radio arrays may detect the 21-centimeter signal from neutral hydrogen across vast cosmic volumes. Because the signal can be measured at many distances and frequencies, it could provide far more independent information than the two-dimensional microwave background alone. It may test primordial fluctuations, early heating, and the transition to the first stars. Large-scale topology searches can use polarization as well as temperature, looking for correlations that chance alignments are less likely to imitate. More precise maps may rule out additional compact shapes or find a pattern too coherent to ignore. None of these programs is guaranteed to reveal whether space is globally infinite. Their value lies in converting broad possibilities into tighter statements. The answer may eventually become no curvature detected below a still smaller limit, no wraparound shorter than a still larger scale, no evidence of a boundary, no deviation from a particular expansion model. That can sound like a list of absences, but each absence shapes the allowed universe. Science often advances by ruling out places nature could have hidden. A detected positive curvature would change the balance. It would suggest a characteristic curvature radius and make some finite, closed models more plausible. A detected matched circle pattern would be revolutionary, providing evidence that space wraps and allowing the fundamental domain to be reconstructed. Repeated galaxy patterns could confirm the topology from a later epoch. A robust change in dark energy over time would alter predictions for the event horizon. The distant future might be less isolated or more extreme than the cosmological constant model suggests. A primordial gravitational wave detection could discriminate among inflationary models and reveal the energy scale of the early expansion. A bubble collision signature, if uniquely identified, might offer evidence for a larger inflationary landscape. Every one of these discoveries would answer a different version of the edge question. The full question may resist a single experiment because edge combines geometry, topology, causality, and origin. Geometry asks how rulers and light rays behave. Topology asks how distant regions are connected. Causality asks which events can exchange information. Origin asks how the space-time history reaches its earliest limit. A universe can be flat but finite, boundaryless but causally divided, spatially infinite but finite in age, or globally finite, while every local path continues smoothly. These combinations are not verbal tricks. They are distinct mathematical and physical structures. Spatially infinite but finite in age is especially important. Infinity of space does not imply an eternal past. An infinite universe can have a finite elapsed cosmic time since a hot early phase. Every point can share that history. Likewise, finite space does not imply a first moment. A closed universe could be eternal or cyclic in some models. Spatial extent and temporal extent are separate questions. The ordinary box picture ties them together. A box has a finite size, an outside, a center, and a history beginning when it was built. The universe need not inherit any of those properties. It may have no center because large-scale expansion occurs everywhere. It may have no edge because space is infinite or closed. It may have no external location because location is internal to spacetime. It may have a finite observable age while its deeper origin remains unresolved. Once these properties are separated, the question loses none of its wonder. It becomes sharper. Ask how far the oldest visible matter is now. About 46 billion light-years in comoving distance under the Standard Model. Ask how wide the observable universe is now. About 93 billion light-years in comoving diameter. Ask whether the universe ends there. There is no evidence that it does, and strong theoretical reason to expect continuation. Ask whether the whole is infinite. Unknown. Ask whether nearly flat space can be finite. Yes. Ask whether there is a region whose signals emitted now will never reach us. Under the standard accelerated expansion model, yes. Ask whether other inflationary domains exist, possible in some models, unconfirmed. Ask what happened at the absolute beginning. Current physics does not provide a tested final account. The honest map contains both measurements and blank margins. Those margins are not all the same. Some await better instruments. Some await better theory. Some may be permanently protected by causality. Knowing which kind of unknown is present is part of knowing the universe. There is a final perspective hidden in the scale of the problem. Every human measurement begins inside a small gravitationally bound system around an ordinary star. Instruments are built from atoms created in earlier generations of stars. Photons enter mirrors only after crossing a history that no human life could span. From this local position, equations reconstruct a universe tens of billions of light years across and billions of years old. The reconstruction is incomplete, but incompleteness is not insignificance. A person standing beneath a dark sky cannot see the particle horizon with unaided eyes. The visible stars belong almost entirely to the Milky Way, and yet the faint darkness between those stars contains light from remote galaxies, microwave photons from the early plasma, neutrinos left from the first seconds, and perhaps gravitational waves from processes older than any star. The apparent emptiness is layered with history. The edge question begins with a desire to look outward until something stops the view. It ends by revealing that sight itself is part of the structure being studied. The observer, the signal, the expansion, and the age of the cosmos cannot be separated. There is no neutral platform beyond the universe from which its complete shape can be inspected. Every possible observer is located somewhere within a space-time and receives only the information that can reach that event. Even a civilization spread across many galaxies would not escape this condition. It could combine a larger set of viewpoints while communication remained possible, but accelerated expansion would eventually divide distant regions. No finite network necessarily becomes an all-seeing eye. The universe may be greater than any account that can exist inside it. That thought is not a reason to abandon the account. It is a reason to make every statement exact. The observable universe is not the whole universe. The cosmic microwave background is not a wall. The Big Bang was not an explosion from one point into pre-existing emptiness. Recession faster than light does not mean galaxies locally violate relativity. The Hubble sphere is not the same as the particle horizon. The particle horizon is not the same as the event horizon. Near-flat geometry does not prove infinite space. Finite space does not require a boundary. And speculation beyond the horizon is not observation merely because mathematics can describe it. Each correction removes a simple picture and leaves a deeper one. What lies at the edge of what can be seen is ancient light. What lies beyond that light in space is probably more cosmos, continuing into regions whose history has not reached us. What lies beyond the limit of future communication is a reality that may continue without ever joining our future. What lies at the edge of space itself may be nothing at all, because space may possess no edge. If the universe is infinite, there is always more distance. If it is compact, distance may lead back rather than outward. If our cosmic domain is one part of a larger inflationary structure, the other parts may remain causally sealed. If space-time emerges from deeper physics, the most fundamental answer may not use the language of places. No version places an ordinary observer at a final cliff overlooking non-existence. The mind can still imagine the cliff. A last galaxy floats behind. Ahead, a perfect blackness has no stars. The spacecraft moves forward and discovers that its path has ended. But to move forward requires space. To look ahead requires a direction. To wait requires time. To see blackness requires light to fail to arrive at a detector. The image quietly rebuilds the universe beyond the supposed end. A true absence cannot be pictured from within a picture. So the most accurate image is not a wall. It is a horizon that remains horizon like no matter how carefully it is approached. A boundary of relation rather than material. On Earth, dawn can reveal that a dark horizon concealed more land or sea. In cosmology, time may allow some new signals to arrive from regions near the present particle horizon. Yet accelerated expansion also removes other regions from future contact. The visible domain does not simply open like a curtain. It evolves. The map gains an ancient layer while losing access to a distant future. This balance makes the present observable universe neither a permanent possession nor a static container. It is the changing intersection of our location with cosmic history. The galaxies in the deepest images are not arranged for us. Their photons began traveling before Earth formed, before the Sun existed, and in many cases before the Milky Way acquired its present form. They arrive because paths through spacetime happen to end here now. Another observer elsewhere receives another selection. Together, these unseen selections may cover a space so large that no shared map can contain them all. There is humility in that, but not smallness. The ability of a local mind to discover its own observational limits is itself remarkable. We cannot see beyond every horizon, but we can understand why the horizon exists. We cannot measure the whole topology, but we can distinguish topology from curvature. We cannot observe the absolute beginning, but we can identify where tested equations become uncertain. The universe does not need to fit inside imagination before it can be studied. Its scale can remain unpictured. Its geometry can be expressed through relations. Its unknown regions can be approached through consequences. The mind does not have to hold infinity as an image. It needs only to understand that no final coordinate is supplied. Perhaps the whole universe is infinite. Then every visible structure occupies an arbitrarily small fraction of what exists, and no traveler reaches a last place. Perhaps it is finite on a scale beyond detection. Then the whole may possess a total volume without an outer surface, and the longest path eventually returns through a geometry that never announced a seam. Both possibilities remove the edge while preserving space. The question, what is actually out there, has a better answer than nothing. There are regions whose ancient light has not reached us. There are galaxies whose present condition can never be known from Earth. There may be domains born from other inflationary histories. There may be topology hidden beyond the largest measurable scale. There may be physics earlier than the transparency of light and deeper than classical space-time. And there are limits that no instrument can cross because the universe is not obligated to place all of its information inside one observer's reach. The last visible object is not the last existing object. The last measurable signal is not necessarily the last physical event. The last useful coordinate on a map is not necessarily a boundary in nature. The observable universe ends where our present evidence ends. The whole universe may not end at all. That is the quiet answer waiting behind the distant galaxies. No wall, no final shore, no outer darkness suspended beyond space. Only the distinction between what has reached us, what may reach us, what never can, and what the shape of space allows to exist without any edge. The cosmos does not finish at the horizon. The horizon finishes our view. Good night.